I want to start by talking about sending a child to his first year in kindergarten. I'm sure all of the parents here thought they will finally have some time to relax and drink their coffee in the morning. But my older sister, who just sent her son Erez to his first year in kindergarten, quickly realized that was definitely not the case. As my sister can tell you, every week Erez comes home sick with a new virus. It seems never ending. She is frustrated and upset, worried about his health, and exhausted from all the sleepless nights. But as someone who researched the immune system, I see things a little differently. I'm actually happy, because I know that this difficult phase means that next year will be much better. The reason that children don't get sick as much in their second year is because their bodies have learned during the first year. Each time their bodies interact with a new virus, the immune system learns from it and creates antibodies, tiny soldiers that will now be present in their bodies and can recognize and fight this virus much more effectively in the future. And in the end of the first year, the immune system has built an army of diverse antibodies that can recognize and attack a wide range of pathogens before they can cause any illness. Now, this defense system is amazing, but it's not perfect. Some people, like the elderly, have old soldiers that don't fight as well. This is because their immune system gets older with them and weakens with age. Others, like those with immune deficiencies, don't have enough soldiers, leaving them vulnerable. And some diseases, like cancer, don't always trigger the immune system naturally. Cancer cells often disguise themselves as part of the body, so no antibodies are made to recognize and attack them. But either a way for us may be to help in all of these different cases. The answer, we can design antibodies in the lab. In fact, this is already happening. There are over 100 FDA-approved antibody-based therapeutics, helping millions of people around the world for a large range of diseases, including breast cancer, melanoma, Alzheimer, COVID, and many more. You can see, for example, in this graph, the big rise of antibody-based therapeutics over the years. But there is a catch. Developing new antibody therapeutics is extremely expensive and time-consuming. Selecting an antibody candidate for a disease can take up to 3 years and cost up to $50 million US. And this is even before clinical trials begin. The reason that this stage of finding the right antibody is so expensive and time-consuming is because many candidates fail before reaching human trials. This means a lot of diseases are left without an effective treatment, and some rare diseases don't get research funding at all. But why is it so complicated to develop new antibody therapeutics? Well, you can think of each antibody as a unique soldier with a different weapon that fights a specific enemy. Each enemy, whether it's a virus, bacteria, or a cancer cell, requires a different weapon in order to be neutralized. But making this match between an antibody and its target is really challenging. Each antibody is made of a unique sequence of amino acids, which are represented by letters, just like in a language. And as I said, each antibody is specific for a different disease. So we can think of it like a safe and a code. Each disease has its own safe, which requires one perfect code in order to unlock and neutralize it. But each antibody is made of a unique sequence of about 200 amino acids. So the total number of possible antibody sequences or safe codes is practically infinite. The number of possible antibody sequences is estimated to be between 1 quadrillion to 1 quintillion. And to put this in perspective, counting one antibody sequence per second will take you twice the age of the universe. So testing them all one by one is definitely not an option. But either may be a way for us to speed up this search. This is where AI comes in. Just like AI can create amazing art and music, why not use it to create antibodies instead? If I tell ChatGPT, for example, to create for me an image of a PhD student giving a talk about his research while the audience is completely fascinated, it will generate for me an amazing image that represents these texts. So why can't I do the same with antibodies? Instead of giving the AI text to generate an image, we will give it the target disease protein. Then the AI will generate for us a new antibody sequence that can neutralize this disease. Now you're probably thinking that creating new images is totally different than creating new antibodies. How can we even compare these two tasks? Well, let's first look at how we train an AI model to generate new images and see that it's not that different. For image generation, we train an AI model, for example, OpenAI DALL-E, on millions of known image text pairs, teaching it the patterns that connect image and language. Eventually, after the model is trained, we can use it to create new images from combination of texts it has never seen before, a new territory. So in my case, instead of training an AI model on image text pairs, I'm training my model, which we called Eagle, on known antibody target pairs, teaching it the patterns behind successful antibody. This allows our model to generalize and make predictions for new diseases it has never seen before, the new territory. But how do we know that the AI suggestions actually work? Well, after training the model, we can generate new sequences for a given target. Later, we can send these sequences to be tested in a lab. And we are already collaborating with several labs, both in academia and industry, from Israel, New York, and across Europe. These labs then give us feedback about which of the sequences actually works against the target. This knowledge can then be fed back to the AI, helping it to improve over time. This approach has the potential to revolutionize medicine. In the future, we could design new antibody drugs faster, cheaper, and with a higher success rate, giving us the opportunity to treat more rare diseases. And during pandemics, we could rapidly generate new treatments. Just imagine if we had this technology during COVID-19. Now remember my nephew Erez? Thanks to his immune system, he becomes stronger over time. With AI-driven antibody design, we can give that same power to millions of people who need it, faster, cheaper, and more effectively than ever before. But until then, I'm preparing myself for a lot of babysitting.